So let's get started. So we'll have two talks this afternoon, and the first one is by Quoc Ho about arithmetic applications of factorization and homology.
Thank you very much for the introduction. And thank the organizers for organizing the conference. It's a great pleasure to be here. So today I will talk, so unlike a lot of the talk in this conference, so the problem that I consider have motivation from mostly from at least from arithmetic and some topology, and if I have time in the end, maybe some representation here. Okay, so let me start with the motivation. So let me start with something classical from number theory. So when I say arithmetic statistics, I mean problems of counting numbers or points on a variety of finite field with certain properties. So from number theory, there's the following classical problem in result in analytic number theory. So suppose we compute the following density. So we consider numbers k less than equal to n, that is square free over all numbers. Then the limit gives you something like zeta 2 inverse. That's the case. This one here is number theory and then representation theory. So zeta of s is product over all the prime of 1 minus p to the negative s. So one might take a slightly different density. So let me consider the following. So let n also go to infinity. When I consider a pair of numbers x1 and x2, so that both are smaller than n and that they are relative prime. Such, and divided by n squared. The interesting thing is that even though the limits we're considering are very different, somehow the result is still the same. So in fact, that's a more general statement that one can make. So let n go to infinity of m tuples of relative n prime. As I will explain what relative n prime in a moment. Over n to the n. Now what you get is zeta of nn inverse. Right, so here, relative n prime means that the GCD of these numbers are not divided by p to the n for any prime p. Okay, so you may wonder what the heck does that have to do with any geometry, because this conference is not about number theory. So let me move to the function field setting, namely, instead of counting numbers, I'm going to count points on varieties that mirror this property. Geometry. So the analog of z, so here we care about z, right? The analog of z is the affine line defined over fq. But of course, I can maybe in algebraic geometry, maybe we may hope for something better. Maybe I consider x to be irreducible, geometrically irreducible scheme or variety over fq.
So I guess you mean zeta of n inverse up there?
Zeta nn inverse. The product of n. Yeah, n times n.
There's an n in the.
I mean, there shouldn't be.
Oh,
k.
yeah, sorry. Smallest thing that has k.
And what is it? Oh, so then I didn't understand. What is relative n prime?
So I fix, okay, so I fix two things, so n and I fix those two numbers. Relative n prime means that the GCD of my tuple doesn't divide p to the n for any p.
The entrance of the tuple are less than 10.
Yeah. So
Okay, I think yes.
And then it's k to the n. Divided by
yes, good. Okay, so now let's move on to geometry. And so I have some variety defined over fq. And I want to replace the numerator and denominator by something. Right? So let me start translating this statement. So what I care about is for limit of n, go let me do k to infinity. Let me use b. Over, so the denominator is going to be symmetric power of x and the fq points of that. Right? So this is x to the d and then quotient now by the symmetric group, and I want to count the number of points on that, and that plays the role of this denominator here. And then the numerator is going to be the number of points on configuration of x. Right, so the difference between the top and the bottom is that here I remove all the things, all the diagonals, whereas here I still have the diagonals. So that's the difference. So here, if you want to talk about multiplicity, here I don't want anything that has multiplicity more than 2. So that mirrors the square-free property of this diagonal. So it's also a classical result in analytic number theory that you get the zeta of x evaluated at this number. So let me quickly say what this is. So again, lim g1, g2 go to infinity. Here is something like this. So that mirrors the pair of numbers, and here I want numbers or particles floating around that has no point in common. This point, and still you have the same color.
So should we know what zeta of x is?
Yes, so let me quickly. So zeta of x, divided with s, is the product over all the closed points of x of 1 minus. So each point on x has the residue field, and I look at the size of the residue field to the negative s and p. So it's exactly like this thing. When I set up p, I look at points on x and look at the size of the residue field. Okay, so let me translate this statement. So here you see that somehow, even though all these spaces look different, the result only depends on the product n. So that's the main feature that we'll discuss today. So now instead of the k to the n, we will consider the following space. So fix n and n. And let D be an m tuple. So the denominator, I would replace it by sim D of x. F2. So this, you can view this as the space of color particles on x. So that's the product of sim di of x. And then the numerator, so essentially you just have to have a subscheme of this guy, a subspace of this guy, satisfying certain relation that you don't allow certain thing to move into the same point. So let me know this space Z M N X. So this is a subspace of the sim B. So such that for all points in X, the multiplicity for each color cannot be or more than n. So this sounds very convoluted, but the picture is like this. So you pick a point on X, right, and they have a bunch of colors associated to them. And you fix n, and you want that the multiplicity, at least one of the color has to be smaller than n. So that's the thing that mirrors the relative n prime. Right, so
color would be the thing for the same
yes,
sim D.
yes, exactly. Right, so the colors are indexed by the. Okay, so now you may wonder why do I move to algebraic geometry. So the thing is that in geometry, whenever I have the point counting problem, you may ask whether it has a homological underlying phenomenon. So let me quickly recall this thing called the Grothendieck-Lefschetz space formula. Okay, so let X be a scheme like before, and then F is some sort of analytic field on X. So we know this calorie to be the color of analytic field on X. Then we can compute the homology of X. So we know this to be the. So for our purpose, for now, it doesn't matter whether we look at the chain or the homology group, but this is the homology with compact support with coefficient in F. And really, technically I have to base change to output closure, but let me sweep that under the rug. And the Grothendieck-Lefschetz space formula says that you look at the trace of the Frobenius on this thing, right? So graded trace with alternating sum. And this is the same as when you sum over all the Q points of X, and you take the trace of the Frobenius at the stop at X. So in particular, when F is a constant shift, we will have the link between cohomology of X and the number of points on X. So here we have a point counting problem. So we may want to ask, for example, can we produce, we can look at the cohomology of these spaces, ZDN or SIMD. We have some chain complex with Frobenius action, right? And can we produce some sort of new chain complex that captures these coincidences that we see in this picture? Is it clear what the problem I'm trying to? Yes, so let me write it down. So the whole is question. So do the coincidences we observe numerically. I have a homological shadow. So now this question over here is a question that makes sense.
What's the subscript of the homology?
C for compact support.
For compact.
Oh, this is star. Just
So now X is over.
So okay, so X is over FQ. But really, for this, I should do base change. So in the Grothendieck-Lefschetz formula, when you do the talk homology, you should base change to FQ bar. Like this. Right. So this question is a question that makes sense in topology as well. Right? So all the objects are defined. For example, modulo the point counting part. For any manifold, I can look at the configuration space that the valid topological space is considered, or the symmetric power of the manifold. And homology is another thing that you can work with manifold. So let me give some known result in topology that kind of tells us that this is not too outrageous a question to ask. So it's a classical result of Siegel, which says the following. So now let's consider the case where X is an affine space. So R2. Switch here and move to the world of topology. Then the result says that if you look at configuration spaces of X, right, so R2, then you take this homology. Then they prove that the homology of these spaces stabilizes when n big enough. So pick a homological degree. When n big enough, that doesn't depend on n anymore. And the homology converges to the homology of the double loop space of the sphere. Okay, so this is the classical result by Siegel and Vassiliev. And another result they prove, you can do the same thing. So sim n of R2 converges to the homology of CP double loop space of CP infinity with the CP infinity. And it's not hard to check that these two spaces So there's a natural map from this to this guy. It is in fact a homotopy equivalence. Right, so okay, so why is this something is related to this? So when X is a affine space, right? And we're looking at say this quantity, essentially we divide it by something that doesn't have any cohomology. Right? So really we only care about, in this case, the problem is about the cohomology of these two spaces. And they say that somehow at infinity, the homologies are the same.
So what's the subgroup of omega 2?
That's 0. So this space has many connected components.
So n and m don't appear on the right at all?
No, this is, so I take the limit when n goes to infinity. And here, n and n both go to infinity. So at the limit, I got this space. It has many connected components, but I only take the one connected, the neutral connected component. Right, so this is somehow a topological manifestation of this point counting phenomenon. So we want to push it further. Namely, we want to have a statement. We want to have a statement that works on this level, but also cohomologically, so that when we take Frobenius trace, we actually recover these zeta values. So that's the goal. And unsurprisingly, this question can be answered using a very concrete computation in factorization homology.
Well, I was going to ask, is this integrally or rationally?
Rationally. Yeah, so I work rationally. I don't know how to deal with positive characteristics very well. So everything is rational. Okay, so let me elucidate the goal a bit more concretely. So what are we trying to do?
So, I know I already asked this, but when you say homotopy equivalence there, do you also mean rational, or do you actually mean an honest homotopy?
No, actual homotopy equivalence.
Okay. But the homology computations are rational.
Yes. So in fact, let me say something about this. So you have a map from S2 to C to infinity, and this is a C star torsion. So when you do double loop.
In the SQ point count, we saw the zeta function appearing. On this side, is there something?
No, but now the goal is to actually unify it and see how the zeta value actually shows. And factorization homology somehow. Essentially, I mean, the deal is that somehow zeta function is defined some sort of product, right? Whereas, so when you look at this quadratic Lasser's trace formula, you see some additivity here. Here is kind of a product. So, at least at the fantasized level, then for factorization homology, you know that this multiplicative excision property. So, the product that you see here exactly comes from the fact that we have tensor excision instead of additivity excision.
So you can spot the Betty numbers.
Yes. Okay, so the strategy. Okay, so before actually saying what the strategy is, let me kind of start with an observation. Right, so we are trying to categorize the process of taking a quotient of two numbers. Right? So usually when you work in say Billion category or triangulated category, and you take the cone construction, right, then what you get is a categorization of the difference, not the quotient. Right? You want to do something that has quotient in it. So let me consider the following observations. We consider this algebra, lambda x. So lambda will be, so let me see what I mean. So lambda will be some either QO more or C. So the few coefficients, I'm going to take my cohomology. So let me consider this ring as a graded ring. Where x lives in graded degree 1. And then I can take the Euler characteristic, the graded guy, where the formal variable I call it t. Then you see that this is just 1 over 1 minus t. So its graded degree, it has one element, or one dimension. So I get this 1 over 1 minus t. On the other hand, if you take this tensor, again, all my tensor, everything is derived, so I will write here, but later on, even when I don't have that, it's still derived. So it's an easy computation. This is first, this lambda in degree 0, and the rest sum with another guy, shifted by 1 to the left. So I always use cohomological grading. So this guy is cohomological degree -1, and this object is in graded degree 1. And now I take the graded trace of this guy. Put it here. T. There you see it's just 1 or minus t. Right, so you see that this is the inverse of that. So what I'm trying to get at is that suppose you want to somehow categorify something to look like A over B. Sorry, it's too long. So suppose I want to categorify something to look like A over B. Then what I really try to do is I should do B tensor with A with lambda, so the derived tensor. So namely we want commutative algebra structure on A and B with appropriate math between them to make this thing make sense. And the claim is that whenever we want to clarify this, we should try to make something like this. So here, right, so the goal is now to equip the cohomology of these spaces with some commutative algebra structure, so that we can take this kind of categorified density. So now actually, back to actual strategy. So let me denote Z M N X to be the disjoint union for the Z D N X. And then I will also use the notation Z of M infinity X. So this is the guy that has no condition. That's notation for the space, and then for the cohomology, I will note them by A. And let A M N X to be the cohomology of X. So collect all the cohomology of all these guys together into one big thing.
You said that your goal would be to have commutative algebra structure on A and B.
So yeah, on this
It
guy.
seems that, I mean, just naively, you're only using an algebra structure on A and just some.
Yes,
module
that's correct. But yeah, that's enough for this problem. But in fact, we can actually have commutative algebra. Thank you. All right. So the goal now is to construct commutative algebra structure on this guy, along with maps like this.
What is ZMNX?
So ZMNX is it's a subspace of sim. So first of all, let me recall. So Z of D and X is a substring of sim of D.
With this.
And this has some extra.
color.
Yes. Remove certain.
Can you say again, what is lambda 1 sub? I mean, I can't seem to be able to do this computation.
This one?
No, forget about this, but lambda plus lambda 1 shifted by 1, what is this? How do you get 1 minus t? That doesn't seem.
That's the one way to put it. That's x but the skyscraper sheaf in A1.
Okay, so this guy you get 1, right? And this guy you get t with some number here. And this is in an odd degree. So that number is -1. because you're taking the trace of a chain complex. So I view this as a chain complex. And for each graded degree, I take the trace of that chain complex. So at graded degree 0, my chain complex concentrated degree 0, so I get 1. At graded degree 1, my chain complex is something that concentrated degree -1.
Oh, okay,
So
okay,
that is
okay. Thank you.
Alright, so we want to construct such a thing, right? And then, okay, so the first gain of doing so is following. So note that when you take H0 of these guys, right? Now it just picks out the connected components of my space, which is just lambda x1 all the way to xn, right? Because the space I started with is connected, where xi is in homological degree 0, it's 0, and then graded degree 1 I, then there's 0 everywhere, and then 1 at I, and then 0. That's to be expected. So now I can use this xi to act on my homology. Right? So xi will act on n x, which has degree 1 now, or degree 1. So now we have a map between different degrees. So at least we can make sense of a homological stability question. Right? Because we have a bunch of groups, we want to have maps to compare them, and we can use this map to formulate what it means to have homological stability. And so that's the first gain we have from having this commutative algebra structure.
So when you write cochains, you're just taking a chain level model of Vattel cochains?
Yes.
And you really need disjoint union there, you're not gluing them in.
No, it's not union.
Sorry, a notational question on the M.
Yes,
We know
sorry.
the ZNF. So I see what the N is. So
Suppose that, then we can, as I suppose, we can prove homological stability. Namely, pick homological degree, and you can have to show that when the di's are big enough, it stays the same. Then we can use this thing, A bar and nx, to denote the stable homology. And then one has to abstract one, so you can show that this thing also has a natural commutative algebra structure, and then one can formulate the following question. Does this thing have coincidences depending only on n, the product? So the first question that we can ask.
Wait, but sorry, this algebra structure, because of the condition that you put, like that at least one weight has to be less than something, does it become nilpotent at some point?
No, so this algebra structure, the one way to think about it is forgetting a point on the space level.
Thank you.
So that's the first question. The second question, so this space is going to have Frobenius action. Second question is to recover zeta values from this object. Right, so essentially there are three goals. We want to prove homological stability. We want to show that coincidence something is satisfied for this object, and that we want the zeta values to reappear after we take the Frobenius space. So that's the more concrete one. Any questions? Okay, so now let me introduce factorization homology. But in an algebra geometric context. So to link with Hero's talk, so here we only take factorization homology of a commutative algebra object. So rather with coefficient in right, so namely corresponding to Hero's story, this is about taking the commutative algebra, forget everything, but just remember the EN algebra structure and take factorization homology of that. So in this, this picture has a slightly easier form to formulate. So let me introduce some notation. So again, shift X is the category of analytic shifts on X. It has a monoidal structure given by this strict tensor. So one way to define it is that suppose I have two shifts on X, F and G. You can box tensor them and do restriction along the diagonal, but the restriction that I'm taking is the strict, the exceptional pullback instead of the usual pullback. So one of the reasons why we use strict pullback, and later on most of the functors are going to be strict rather than usual, is that somehow we're dealing with homology rather than cohomology. Up to a radial dual, we are dealing with them. But technically, it's more convenient using the strict functors. So now that we have a symmetric monoidal structure on sheaf on X, so again, this is really stable infinity category, symmetric monoidal category. We can talk about commutative algebra objects in this category.
What is X?
Sorry.
X can be anything.
Yeah, X is any geometrically irreducible variety over Q.
So commutative means E infinity, right?
Yes, commutative infinity.
So Quoc, do you really want A and N in that cohomology, or is that infinity? Above.
Here?
Or more up? Yeah.
Yeah, this is the same. So this is the space.
Thank you.
Okay, so I look at this category, and I look at COM algebra. So when I say COM algebra, I really mean commutative algebra objects in vect. And by vect, I mean really the derived one, not this chain in Hero's style. So I have a map from X to a point, right? And let me call this map pi. So pi up a strict, right, will bring a chain complex to complex of sheaves on X, and it's symmetric monoidal because I'm pulling back using this functor. So it automatically upgrades to a functor between the commutative algebra categories. And by abstract nonsense, so essentially some presentable category nonsense, I want to show that there exists a left edge. So note that the left adjoint, and denoted by pi lower question mark, is not the usual left adjoint, which is the lower strict, because lower strict doesn't behave nicely with respect to tensor structure, so that wouldn't give you a commutative algebra object if you just apply it to a commutative algebra object on the top. So it's something new. And in fact, the pi lower strict really implements commutative algebra factorization homology with coefficient in the commutative algebra object. So that's where factorization algebra comes in.
Sorry, and you said this is commutative algebra in L.
Yeah, so QL vector space. Yes. Or if you work over C and work with the manifolds, then you can look at sheaf equation in C. So then this can be C. So essentially, as long as you have 6-functor formalism, everything goes fine. I'm just more used to fitting in schemes. Okay, so why do we care about this functor? Right? So the preview. Okay, so essentially the result. Actually, let me before saying that, let me do some notation. Right, so eventually, these algebra are coming from these color configuration spaces of X. When we factorization homology of X, we coefficient in a very simple algebra, commutative algebra. Maybe now, now I have to be careful. I'm going to have straight, A straight, and then here should be curly. So the curly guys are homology, and the straight guy are coefficient. So this thing is just x1 over to xn, mod out by x1, xn. And if you really care about point counting, so I have to tell you where these things live. Yes. So xi is in degree 1i, so graded degree 1i, cohomological degree negative 2d, 2d. And so the reason why I put 2d there is that eventually I will strict pull back to x, and this is somehow after you strict pull back you get something in degree 0. That's why it's off like that. And then if you care about point counting, then we take this. So this is just for if you're interested in recovering the zeta value later. So this is twist how much Frobenius is acting on the vector space. Okay, so the theorem says that pi lower question mark of pi upper streak of straight a m n is naturally equivalent to a m n x. Right, so this is a simple example of how factorization homology gives you cohomology as some very familiar object.
What's d in terms of capital X? What's lowercase d?
Oh, yes, sorry. This is dimension of x. Okay, so now.
By implementing factorization homology, you mean you're taking global sections of something on the Ron space of X?
Yes, so that point of view will make it clear why we see these configuration spaces shown. Okay, so let me make a remark in case you actually work with factorization homology. So the remark is that I think it's a theorem by Ayala and Francis, who says that when you take the factorization homology of a manifold M with coefficient in a free En algebra, say Q, doesn't matter really, then you recover the homology of the configuration spaces of M. That's a one color. Right, so here's generally an En thing. Whereas here, right, if you're actually familiar with this story, then you might wonder how come everything is commutative instead of En. So the answer is that the two approaches differ by an En Kouzou duality. The upshot is that even though these things, so for this particular case, it's simple because when you do En Kouzou to a free object, you get a trivial object. So in the case of one color and configuration space, right, the algebra you get is this algebra, which is the trivial algebra, commutative algebra generated by one element. So that's kind of the relationship between Ayala Francis story and this commutative algebra story. But somehow, for configuration space purposes, commutative algebras are much easier to deal with. Okay, so now let me introduce the Ron space perspective. Right, so here, the way I define the functor pi lower question mark, I define it in an abstract way, so it looks like it's hopeless to have any computation or link it to any other kind of geometric object. So the Ron space perspective will remedy that. Okay, so let me introduce this construction. So we call it the delta question mark construction.
Okay, this is a great suggestion. Instead of calling it delta question mark, you should call it
Delta shrug.
How do I?
You're ready to say.
Same notation.
But like you
Shriek
shriek
means
Oh, shrug.
exclamation mark, shrug means
Oh,
question.
okay. I will say that. Delta shrug.
Why is it a small delta and not a big delta?
Because somehow the run space is very infinite dimensional, and X is like, so the run space is going to be moduli space of as many points on your manifold as you want, and X has 1 point, so it's very small. That's not a mathematical answer. I didn't choose that. It's not my fault. So in fact, so this rough thing. So originally it was in the notes of Louis' course at Stanford. That's why he used that in the paper. What they actually wrote up, they don't use anymore. But it got stuck with me. Okay, so the running perspective. So this thing. Right, so eventually this is going to be a functor from commutative algebra object on shift on X to shift on Z and infinity X. So it's a little bit more. In fact, it's going to be some commutative algebra object in this category with some another structure, but for the purpose of explaining why these things appear, let me just leave it as that. Okay, so what is this supposed to do? So let me take a step back and talk about how we think about EN algebra shift duality. So suppose you have so let A be an EN algebra.
So Quoc, does a delta shrug exist for every M?
Yes. Sorry, so I'm a bit sloppy here. So really here I should take graded objects in here. And they're graded by M color. So yeah, so I'm a bit sloppy here. Okay, so suppose A is in the EN algebra. And let M be an n-dimensional manifold. The goal is to somehow encode the EN structure. So again, my EN algebra, I mean EN algebra in vect or in chain complexes. So I want to encode the EN structure as sheaves on powers of n.
Is this n supposed to be the same as the dimension of the manifold itself?
Yes, just like D. But D is the dimension. I don't know.
Yeah.
Okay. I don't know what to write. So, right. So now I want to produce something that lives on n. Right. And so now, the shiftiness of the resulting object should capture the multiplication structure of this EN algebra. So let me just do when k equal to 2. We're not really doing any honest homology here. I'm just trying to motivate the picture. So when I look at the 2, we have the following thing. So instead of thinking of 2 copies of a disk mapping to a disk, right? So in the EN algebra is like this. For each embedding of this thing into another thing, you get a multiplication. So I guess one way to think about this is that you think of your n square is like this, right? And this is the diagonal, and you have points floating around on. So you have points on the complementary diagonal, say that parameterizes 2 points on n. And whenever 2 points collide, right, which is a way of saying this somehow, when this thing moves to the diagonal, you get multiplication. So in other words, one might capture that by saying that let A, you box tensor twice, right, and you restrict to the diagonal, the complement. Let me say what I mean. So this is the diagonal, and this is the complement. This is the open complement of the diagonal. And I'll do this. Right, so if you look at the co-star of the point at some point on the diagonal, right, this will pick up homology with the second configuration spaces of Rn. And such a thing, right, multiplication map becomes a map like so.
Sorry, is that I or delta?
Thank you. A map like so. So put A. So I do A is a constant sheaf on N. And then I want to glue this A and diagonal with this A box tensor on the complement diagonal to get some sheaf on N squared. So if I do it, I do this. I call it A2. So this guy has the property that when you strict pull back to the diagonal, you get back A, and when you strict pull back to the complement diagonal, you get A box tensor 2. So you can imagine that you can do this thing for higher k, and you get a bunch of sheaves on powers of n, right? And that's give you a way to think about En algebras as sheaves on powers of n. Right? There are going to be some Sn equivalent thing that leads to configuration space, but that's the idea. Okay, so how about so this is the En story, right? How about the commutative story? It's slightly simpler. So now, so instead of this thing here, so this thing says that for each time I want to multiply, I need to also keep track of some element in the homology of the configuration space. Now I have commutativity, I have a commutative algebra, so I don't need to keep track of that anymore. So really what I have now is something like this. Okay, so if A is inside algebra of sheaf on X, right, then multiplication is something like this. From tensor to the same. That's the multiplication map of my commutative algebra. Then I now do the same thing. And get this guy. So this is how you would implement this functor. So this is kind of the picture for n square. But one can imagine that you can do a similar thing and get all powers of n. So this is how you construct it. Okay, so let me do a simple. Let me do two examples. One is this guy, and one is the symmetric algebra. So let's start with this object. So here I kind of said the story for the non-graded version, but for the graded version, when you do this, you need to keep track of the total grading that you put on this thing. So for this guy, right, say in graded to be 2. So on x squared, what you have is that on the complement of the diagonal, you have to put two things of graded degree 1 so that they sum up to degree 2. And on the diagonal, you put one thing of degree 2. And the multiplication map is just a constant map. So you're gluing something along a constant map. So what you get is that A2 is going to be just a constant sheaf on x2. And because this thing, all the multiplication map are just constant, when you glue them, you get all the constant sheaf and all the xi. And so that's why when you take factorization homology of x with coefficient in this guy, you just get symmetric power of x and nothing more interesting. So that's the first example. Now let's do this example. Right, so for this example, you see that you have the following. So on the complement of the diagonal, you have something like lambda. So this thing you put lambda. And the multiplication map, right? You put something of degree 2 here. But in this thing, there's nothing of degree 2. It's 0. So whatever you put here, you get a sheet. Not just a star extension of the thing on the complement diagonal. So note that here, when you strict pullback of your guy, A2, you get 0. So you get a sheet that somehow, strict speaking, only support on the complement diagonal. That's why when you take factorization homology, you recover the configuration spaces.
So Quoc, so to make sure I understand, is this some version of implementing causal duality? Like the thing that you've described on x squared looks like the causal dual algebra generated in degree 1.
Which one?
The fact that lambda constant sheaf on x squared is 8 parens 2. Is that a statement that there's some causal dual to?
No, there's no more causal dual here. So somehow the fact that I use this, this already in the other causal side. So here there's no more causal dual.
Okay, well that's
the homology of configuration spaces. Okay, so how about density? Can we already see something about the density? So it's actually now pretty formal. So note that this formula is defined as a left adjoint, which preserves push out, and push out in the carrier commutative algebra is a static tensor. And so if we're interested in this thing, so we're interested in this thing. Which is the same as that theorem. So the same as and so the problem becomes looking at coincidence phenomena exhibited by this guy. Right? But this guy is now very simple. So this guy is just lambda x1 to xn divided by x1 xn to the n over the symmetric algebra. And if you remember the correct rating and t-twist, you will get something like this. Some shit that I remember, but the important point is that the t-twist is dmn, where d is the dimension of x. So this dmn is the source of the zeta value dmn that we saw in the beginning. So, and so the remark, how to link factorization homology to zeta values is that suppose A is in commutative algebra of sheaf on X. Then one can do the following: trace of the Frobenius. So assuming that certain things converge. Let me do great version. With the formal variable t. This thing becomes the trace. Right, so this is how. So we have a product expansion for zeta values using factorization homology, and that's how. When we essentially applying this, you see the dmn show by looking at the features. Okay, so handling of these abstractly defined guys, right? Because eventually, right, we want to say something about the homology of the configuration spaces themselves. So the story is about something called causal duality. Quickly see how that comes in. So to compute these things. And so, for example, to prove this formula, for example, or to prove homological stability, one need to use causal duality. So again, here we don't actually need to use much about causality. The only thing we need to use is the fact that there's an equivalence of category between commutative algebra and something called Coley algebra. Coley-Cohen algebra. So in the graded setting. So essentially we're working on essentially positively graded stuff. So the category involved is something called the technical term is polytopic. You don't have to worry about this, but essentially, so this theorem is by Francis from Gitzberg. Okay, so what we need to know is about this equivalence is that it exchanges free and trivial objects. Right? Namely, suppose you saw something in here, and you want to look at this thing in here, right? There's a way to kind of filter this thing so that in the end, you get something that is filtered by free object. And then so you reduce the problem, a lot of the problem here, to the statement about free object. And then it's easy. Right, so that's kind of the shape of how we actually can compute these things. So let me, now that I have 2 minutes left, let me say one more thing. Because I have some representation theoretic interest. So here, I look at unordered configuration spaces. But how about order? So when you want to look at this space Z, M, N, X, tilde. So before I quotient now by the action of this Sn, right? Now I don't do that. So now this thing, right, is this joint union, and it has action of symmetric group. So the interesting question is how to study the representation of S of the symmetric group that show up when we go to field, whether there's some sort of stability and representation that appear. So here, so it's work in progress. Is that actually it's not too far from what we already did already. So instead of grading everything by this category, we replace it by a category called F set, ISO, graded objects. And so more concretely, we should take factorization homology with coefficient in commutative algebra objects in this category. So this that has a modular structure, and this thing also has a natural modular structure by just this joint union. So you sometimes make convolution to cook up a new modular structure here, and doing this you can kind of repeat the story and analyze what stability of representation of symmetric groups that appear in homology of these. Thank you.
Any questions?
Yes, except that it has to be commutative. Otherwise, when you go back to x, you forget too much data.
So it has to be fully commutative.
Yes, fully commutative.
So you can't take the general EN as
Yes, then you cannot. You have to work with the whole round space. Which you generally do.
sorry, you have to have the infinity to make sensible definitions, or you mean in your examples?
Which example? So okay, so
The question is this a sensible construction that I can do with any EN algebra, or do I
yes, the
need-
construction to so there were two constructions. The first construction works for any EN algebra. But from any EN algebra, you can cook up something on the round space. Now the thing is that the thing on the round space that when you restrict to just x, you get the equivalence of carries when you look at just commutative algebra. And the equivalence of carry is not true anymore. We just look at generally just the EN.
Is there an example of a computation that you can do now that you definitely couldn't do before?
Yes, so a lot of these spaces, so for example, so there are two things that so before people could do when x is smooth, for example. And when x is not smooth, we don't know how to do it, and this we do a very simple way to actually essentially the same result without any combinatorics. So before, so a lot of combinatorics to actually say something about these spaces. And then one more thing is that I have this number n. This can actually be generalized to a tuple of n that have kind of different threshold for different colors. And you have the same result without actually have to do a combinatorics.
Any other questions? Okay, let's make the speaker. There's a coffee break, and then we start again.